We are excited to present Agnathax, a specifically designed undulatory swimming robot, with the goal to help us understand how the nervous system in vertebrate animals generates locomotion. Let's start by taking a closer look at how animals like the lamprey swim in the water. They do so by sending waves of body bending from head to tail. Thereby they accelerate the fluid backwards and the body forward. From previous work, we know that these waves are generated in the animal's spinal cord, which is part of the central nervous system. Here, groups of neurons, called neural oscillators, generate the corresponding rhythmic muscle activations that eventually lead to undulatory swimming. In contrast to the central, there is also the peripheral nervous system, which is made of sensory neurons that provide information about the state of the body and the environment. In this study, we were interested in the lamprey's ability to sense the surrounding fluid as it moves. More specifically, we were interested in understanding the pressure forces along the body as the body swims through the water. Our guess was that these external sensory inputs from the fluid outside could locally influence the internal neural oscillators inside the body of the swimmer by a process called entrainment. Entrainment is a well-known phenomenon present in many fields from biology to engineering, in which coupled oscillating systems interact with each other and are driven to a coordinated state with a common frequency. To explore this idea of entrainment, and because this is difficult to investigate in a living animal, we designed Agnathax, which serves as a robotic counterpart to the animal. The robot is constructed out of a series of segments. Each segment has a motorized joint that allows it to generate side-to-side movements. In addition, each segment has a sensing unit to measure the side-to-side forces that are generated between the robot and the water. To understand the effect of entrainment by the measured interaction forces from the water, we put the robot in a purposefully disorganized state first. More precisely, we removed the internal connection between neural oscillators, so each of the segments acted for itself, independently from the others. Without the help of the sensed forces, this led to a bad swimming performance. Incorporating the sensors with the entrainment, though, generated a beautiful traveling wave. Internal connections between the segments were still absent, but coordination emerged as the fluid dynamics naturally shaped the forward swimming movement. In a second scenario, we looked at a case where the neural oscillators in the spinal cord were turned off, however connections were present and internal timing between segments was preset. Here we found that the entrainment mechanism could induce the missing oscillations and again lead to coordinated forward swimming. Together, these results indicate that the force sensing provides both the ability to coordinate and generate oscillations along the body redundantly to the internal neural oscillators. Subsequently, this redundancy led to an increased swimming robustness to neural disruptions and highlights the added benefits of the nervous system with both central and peripheral components. Our results can possibly explain how lampreys and eels can still swim after spinal cord transections and point to the importance of sensory inputs in shaping locomotion patterns. We also expect that our model of central and peripheral control can help design highly modular robots that are remarkably fault-tolerant and robust against damage in their communication buses, sensors, and control circuits. Such robots could be effective in search and rescue missions or environmental monitoring.